Good afternoon. This is Local Power Sourcing, the promise of microgrids with small modular reactors. My name is Jim Riley, and I was selected to be the moderator of this panel. There's only one other person, because the third person, who's with Zandi in San Diego, his airplane developed a technical problem with its floor. It was a Boeing, and they said that they were going to repair it in 4 hours and then take off and come here. And he said, I think it wasn't a good idea. There were no alternative flights, and even if I did make it, I would have been too stressed to talk to anybody, even you, Jim. So we don't have Michael with us, but he's worked very closely with Tim and with myself. We have his slides and his comments, and he apologizes profusely for not being here and hopes to address you all at another function. I come to the data center world after the past 3.5 years from the power system engineering side. I'm a senior member of the IEEE Power and Energy Society, and I've been involved with standards for the IEEE Standards Association for microgrids, the integration of distributed energy resources into the grid, and the management systems for it. We worked with a number of vendors who are working on data centers now. One of the major ones, which is here on the energy management systems of both the microgrid, which in this case would include a data center, and the management system of the distribution utility that you're communicating with. And just to start off with a little point, no matter where you are out there, you're connected somehow to the grid because you're part of the power delivery system. And it has an impact throughout. I'm very, done a lot of work in the area of reliability standards, worked with the North American Reliability Corporation, who does the standards for the grid, the operating standards. And in turn, they report up to FERC, which you're all familiar with. Done enormous amount of work with reliability, exercises with the ISOs, the guys that run the grid, for natural gas and electric interdependency. There's a lot to learn there. I heard a presentation at the main hall on natural gas, and there's a lot to learn about how to deal with the natural gas industry directly. For microgrids, combined heat and power is more than 50% of the microgrids. It's closer to 80 in some areas as a microgrid. It's very important, the dependency that it has on natural gas, if you will. And that seems to be a technology that's of greatest interest. Also, I'm responsible for the standard for microgrid controllers, control systems, which we're revising now after 10 years. It will have an annex related to energy management systems for data centers connected to the distribution utility and to the grid. These relationships are written in an annex to the interconnection agreement that I've heard a lot about here. And the interconnection agreement is one thing, but another thing is the rules that go along with it that you have to follow in order to maintain stability. And one of the most important points is not the dispatch of power one way or the other, but the transition back and forth, because you can collapse yourself at both sides. You can actually collapse the entire grid if you're not careful from a very small part of the distribution system. I've noticed and got interested in data centers because it's one of the most important loads out there and a very big impact on reliability. Also, microgridding of data centers is one way to supply it with local power, and so that you have the independence and the supplies that you need in emergencies, if you need island or that sort of thing. And it was the next big challenge on the list, and it's a really big one, and it's growing now. So I want to try to solve the information gap to a certain extent between the data center industry and the power system engineering group. And I'm on the working group of the International Atomic Energy Commission, SMR, the working group for the roadmap for SMR And it starts with natural gas generators, and one of the most major loads that's part of that roadmap is going to be data center loads and serving them, which is an international issue. So I wanted to explain just briefly the meaning of the session title. Local power. What are we thinking of when we're talking about local power? I didn't want to say like on-site or behind the meter or any of those, because there are a lot of different ideas about how that really works out, and a lot of misinformation, by the way, about how it really works. But it's basically generation that's installed on site or remote from your site and connected by some sort of communications or electrical network. The boundary does not have to be physical, it could be electrical, if you will. And it can, of course, disconnect from the grid, an island under certain circumstances, which are highly controlled for one of the reasons I mentioned before. You can actually collapse the system and actually damage your own equipment. Now, what is the microgrid? Microgrid is a term that is so misused. Most people will call anything that has backup power a microgrid. So therefore, because you have these megawatt level diesel generators at data centers and you can run for a while without the grid on them, you're a microgrid already. But the data center industry hasn't been so absurd to attach that title to it. But nowadays, you know, it's a word that's out there. It's almost a buzzword. But the definition that's in the IEEE for the controller is what you see up there. We don't want to go reading it, but it's a group of interconnected loads and generation that can operate and survey your particular load pattern or part of your critical loads. It doesn't have to be all of them. So that definition is very important. But what's most important here, and getting the data center community connected with the power industry, is the interactivity. The whole idea from the beginning, 12 years ago, when the Advanced Microgrid report was written by Sandia National Laboratories, the whole idea there was it's an interactive grid across the point where the data center meets with its generation, if you will, meets the grid itself. And you have exchange of power back and forth. That's been the idea for 12 years, but it's never been done that way. It's usually been done for resilience, because people were always saying, well, what if we don't have the power? What are we going to do? Oh, we're going to talk about it in terms of local generation that can be used to disconnect from the grid. The ideas that we're proposing here, and what I've been working on for 12 years, is to make it interactive. And by being interactive, there's money to be made by participating in markets under certain circumstances, but you always have to take care of your own load first. But there's a lot of money to be made if you handle it properly. And there's also ways that you can contribute to the actual operation of the grid and its stability. And they're really generally not well known and never discussed. But if you think that transferring your load from one data center to another is helpful, it could crash the grid. And there's a lot of talk about that in the regulatory body for the grid, the NERC, if you will, and FERC. And you know, there's a big docket about Susquehanna and behind the meter thing. So there's rules that apply to all this, but there's no reason why working those rules out together can't bring these communities closer together. And this would increase the value of the relationship. It would solve a lot of the resource adequacy, lack of generation, and would also give you a lot higher reliability on a system-wide basis. So that's all about what the microgrid is here. Now, the small modular reactors, Tim's an expert on that. He's a nuclear engineer. But from what I know from going to Vienna and everything, there's like 80 different ones, and some of them just exist on paper. And it's not going to be available to be used in any significant way, especially smaller ones, until they're actually proven in the field someplace. There's data and they're all approved. Well, you're looking at 2029, 2030. There are a couple of large locations where there's going to be available uprated plants like Palisades in Michigan. But basically, if you're talking about as part of the industry's nirvana power source, you're looking at from 2030 up to 2035. So one of the things that we've been doing in what you're going to hear about here is how you actually start with something you can use now with natural gas and then take advantage of all the characteristics, the special operational characteristics of nuclear reactors. So you won't have a stranded asset, and you'll have something that you can add on to as power grows because they will be integrated. So we're talking about bringing two industries together and setting up a line of communication. We have a working group in the IEEE that for the first time includes power system engineers with data center folks, the power system people with the nuclear people. Tim is one of them. One's from Chalk River up in Canada, which is more advanced than we are really. And the third one is from Idaho National Laboratory. Now, about the scale of microgrids, microgrids can be in a megawatt level. Don't think of it as a standby generator. Don't think about the Generac at your house. It's a power system that serves load within a specific boundary and has certain control systems on it that actually define what it can do under what circumstances. It can be in the hundreds of megawatts. There's actually some talk of futurists in the power industry where microgrids might actually be what the distribution system evolves into. But it won't be a community microgrid like you've been hearing about. It will be islands of generation and load matched, and that load could very well be a data center. But here you're talking like forecast of 15 years out. So don't think of it as a small unit. It can be 100 megawatt. There's a microgrid that's 55 megawatts, White Oak right here in Maryland, the Washington border. And it's been there for 20 years, and it's because PICO from Washington said, we just can't supply the power to you, so you'll have to do it yourself. So they developed their own CHP, and it's been running for 12 years. It's a Federal Drug Administration. Got all kinds of stuff that if you lose the power, all these 20 years of scientific research can just disappear. So it can be very large. So with that, that's an introduction and a context to this about how the power system engine needs to get together with the data center industry and then bring in the nuclear folks so you're prepared for it, you plan for it. You can plan for it today, but not on the basis of an expectation that's unreal. Play for it in a way that you're not going to have a stranded asset and you're going to be doing something good now, and then you're ready. So that's what the philosophy is behind this. And with that, I'll say this is, Tim, it's not changing here. This one here. Counterintuitive there. This is the three of us. Yeah, poor Michael didn't make it, but I'm glad he didn't get in that plane. He stayed, and then they had an earthquake. This is Illinois here. So this is us, and our contact information is on the last slide. It needs to be available to you. We're going to have Tim go through the slide deck. He's a teacher, so he's very good at that. And then we're going to have Q&A later, and you're supposed to come to the mic to ask the questions. I'd love to have a wide-ranging discussion with you all, because an area would like so much to communicate to this community. Tim.
Thanks, Jim. Hi, everyone. Yeah, I'm Tim Grunlow. I'm a research scientist at the University of Illinois, focus on research about deploying reactors, which we'll talk about. So nuclear is something that's been getting growing attention. We'll talk a little bit about the benefits. I would be remiss to not do that. I'd probably get in trouble. But also, I think probably everyone's heard about the benefits of nuclear, so we also want to talk about some of the realities and how we can plan for those realities and how we can optimize against those and really take advantage of the opportunity of nuclear. There's talk of when is nuclear going to be commercially available. I have on here that it looks to be commercially available in 5 to 10 years. I want to be really careful with that point because the AP1000, for example, is available now. You can talk to reactor vendors and you can sign contracts now. So they have very advanced designs. By commercial availability, I mean that if you take a snapshot now and you look 5 years ahead of time, the regulatory landscape is going to be much more advanced, although the designs may be quite similar, and supply chains are going to be a lot more built out. So that's a top level on that. Advanced reactors potentially offer really decreased deployment times, which we're very excited about. There's a NEI concept called RIDRA, which they're identifying regulatory approaches to get certain reactor classes deployed in 6 months. So, if these things can be realized, the market for advanced nuclear is huge. And I also want to make a point, we are at the university, I'll talk a little bit more about this in a bit, but we're working on deploying a reactor on campus now. So everything that we're about to say comes from kind of a boots on the ground perspective as well. So, the benefits of nuclear, we like to talk about capacity factor. So these are data from the EIA since 2014. And so since then, nuclear has maintained a capacity factor around 92% fleet-wide. Some of the highest performers are around 95%. We're very proud of that. And so that is kind of in a class of its own in what nuclear can do. Nuclear is also potentially an extremely long-lived asset. So of the reactors that are operating now, the average age is about 42 years. The oldest is above 55 years. Currently, licenses are slated to expire at 60 years, but there's very serious talk of uprating to 80 years. There's a lot of work happening. And there's also serious talk of, after that, uprating to 100 years. And so, nuclear looks like it's going to last a really long time. And, as we move into kind of this next generation of reactors, they look to be increasingly self-reliant. So this idea of bring your own power looks to be more and more possible with advanced reactors. We have smaller footprints. We rely on other things a lot less. So, current reactors need to be near a large body of water, a river, or a lake, or an ocean. Some advanced reactors don't need that. Some advanced reactors, really don't need anything to make sure that they can operate efficiently and safely. And nuclear also has a strong track record of safe operation that we're quite proud of. So one way that you can tell that the winds have shifted in nuclear is, 10 years ago, the first question people would ask me is, how do you know it's safe? Now the first question people ask me is, how much does it cost? And the answer is there's a lot of uncertainty here. So I've highlighted some publicly available data that I use the most, emphasis on publicly available. So if you're speaking to a vendor, keep in mind that they have access to proprietary quotes. They have done long lead time procurement planning. Their numbers are better than this. But what this shows is, importantly, sensitivities. So the reactor cost is, we generally scale it against energy level. And you have large reactors have one cost function, small modular reactors have another cost function, and then microreactors have kind of a third cost function. And what you see is the dependencies of that cost change with the size of reactor also. So very large reactors, the costs tend to be all about CapEx, and then smaller reactors, there's O&M is operations and maintenance is potentially a larger percentage of the cost, because you're bringing a lot of that CapEx into a centralization or into a centralized facility. And then there's also lots of different technologies out there that are going to be a bit different, but the industry's in a strong position to quickly go down that learning curve after we get some of these deployments going on. And these deployments are going to be key. So there's several high-profile deployments. Some are publicly funded, some are privately funded, which is a very exciting thing to say in nuclear, that a lot of things are happening. And these will exercise supply chains, and they will decrease the uncertainty very significantly in quite a short time. And so I want to talk a little bit about the project that we're doing at the University of Illinois. So what I'll be talking about after this is how are we trying to optimize reactors? How are we trying to maximize energy efficiency, maximize economics? And a lot of this is coming from we're trying to build a reactor. So we are working with nanonuclear on this, formerly with this MMR technology, formerly USNC. This is a high-temperature gas-cooled reactor, and we've been engaging with the regulator for quite a while now. So we've got successful outcomes on 5 TALPA reports, which, if you're not familiar with the regulatory process, a TALPA report is basically a section of your license that's already approved. And then quite a bit else. We've also been working with site development. So I'll talk a little bit more on the next slide about the UIUC campus and how we have a a combined heat and power plant on there. The plan is to tie directly into that and demonstrate co-location. And another point that I want to make, so this reactor does have one vendor, but we like all reactors, and we want to use this to benefit not just Nano, but all reactors. So once this is deployed, we're going to do operational research, we're going to make data available, and we're going to do everything we can to help reactors operate efficiently and safely, and approach all these very interesting applications. So now we're going to start moving into, what does an optimized deployment look like for a data center microgrid? So I'll talk a little bit about UIUC campus microgrid. And so, if you've been to Champaign-Urbana, it's a standard college town. What is a little interesting is we have Abbott Power Plant, which is natural gas, coal, and fuel oil, which provides 100% of our steam needs. So it is primarily a district heating system. It provides about 50% of our electricity needs, and it also provides chilled water. It can operate in islanded mode. It has several times. That's one of its requirements to operate the full campus in islanded mode. We have hundreds of buildings. We're going to focus on one of them in a little bit, which is the Blue Waters petascale supercomputer that operated on our campus. We also have a bus system that operates hydrogen buses. This is kind of an interesting scoping study that we did. We spent a lot of time working on how reactors are going to integrate with different applications. So one of them has been hydrogen. Turns out about a 10 megawatt reactor, give or take, is enough energy to generate hydrogen for the bus transport system for a city the size of Champaign-Urbana. So that's an interesting way to decarbonize or bring in fuel security for something like transportation. So our microgrid, we have electrical, thermal, transportation, chilled water needs, and we have a lot of data on all of these, which we're going to use here in a bit to do some optimizations. Here's what the data look like. We have 8760 data, and it's actually a little bit better resolved than that, but for this we used 8760 on most buildings. On the generation, we have electricity that's provided by Abbott Power Plant, by the grid, by 2 solar farms, and by two on-campus solar farms, and by a nearby wind farm that we have a PPA with. We have steam demand, we have high pressure steam, and we have low pressure steam. Low pressure steam fulfills our district heating and does some other things. And so to look at what a nuclear reactor powered data center microgrid looks like, we took the Blue Waters supercomputer. We took a year's worth of data from that. We'll show a little bit more about that, but it's both electricity and cooling data, and we modeled a bunch of different scenarios on how you would power that. The system was an NSF-funded facility. It operated, it was originally planned to operate for 5 years. They operated it for 9 years. It's been replaced since then by the Delta computing facility, which has recently been expanded into the Delta AI facility, which has a lot of GPUs. So a very exciting asset for us on campus. For a while, it was the largest supercomputer in any university. So we were very proud of that in Urbana-Champaign. We also built out a very large amount of chilled water cooling for it. So if you're ever in Champaign-Urbana, you've probably seen it, maybe didn't recognize it, but there's a very large water storage facility for chilled water right next to that. And what this allows us to do is optimize or what this model that we're building is allowing us to do is optimize what a data center with actual load data, actual cooling data, what that optimal configuration would be based on what metrics you're trying to meet. And we're looking at this from an integrated co-deployment model. So a lot of topics that have come up at this conference so far are bringing your own power. You don't want to wait for the utility. Let's build your own energy. Nuclear potentially offers a really strong option for that. And then how can you improve the economics? So CHP is one great way to improve economics. Talk a bit more about that. But I drew this little cartoon down here. So what we're looking at is, you have a nuclear power plant, you have a data center, you have electrical generation, and you have several heat streams that go around and do different things. And can you, optimize these different streams to lower your cost basis, or I guess on the other side, for a given, power technology, how can you get as much compute for that as possible? So I promise I won't talk about thermodynamics very much, but a nuclear reactor, like a coal power plant, like a natural gas power plant, is a thermodynamic cycle, which is about 33% efficient. It can get up to 40% or so, depending on the cycle that you use. But what that means is for every 3 units of thermal energy that you release from your fuel, only one of those units becomes electricity, 2 become low-grade heat. And if you can optimize your application to use that heat, then your efficiency goes up to like 80 or 90%. And this is what Abbott Power Plant on our campus does. So in that case, our application of that heat is district heating. So we put low pressure steam, fairly low temperature steam through a bunch of buildings. We run autoclaves, we run kitchens, we do lots of things with that. So a topic that's been coming up, it's been mentioned here already, is using absorption chillers for this. So absorption chillers are another thermodynamic cycle. And there's some off-the-shelf equipment that's available. But what we're looking at is, of all the technologies out there, some reach certain temperatures, certain pressures, certain coolants, that kind of thing. So they're going to have their own unique thermodynamic cycle. And then the absorption chiller is going to have its own unique thermodynamic cycle. So there's really interesting optimizations to be done there. For our analysis, we did a really really basic first shot, where we just took the waste heat, we applied that to an absorption chiller with a coefficient of performance of 0.7, and then we looked at some of the dynamics of what that offers. We'll show that later, but I'll give you a hint. It looks like it saves 10 to 20% of the cost basis for the assumptions that we made, being able to utilize that waste heat, which is potentially 20% more compute. Here's our electric demand for Blue Waters for a year. It has kind of a unique profile. So some of this is just due to seasonal demand, but actually, so it was a supercomputer. So sometimes some folks had very large jobs, and the HPC scheduler would stop scheduling small jobs in the run up to a very large job. So that's why you see some of these dips. And so you'd scale down, you'd scale back up very quickly. You get some spikiness on that. The thermal demand, in this case, this is showing the chilled water that the facility used for the same year. You see that the winter and the summer look very different. So Blue Waters also had evaporative chilling. And this is data that looks very similar. So sometimes the evaporative chilling is enough, other times chilled water has to come in. And so you can see, if you have a facility like this or something that scales like this, sizing the equipment around this is going to become non-trivial. It's not enough to say I have a 100 megawatt data center, I need a 100 megawatt reactor. It's, what is the equipment accompanying that? What does all that look like? And so here's where I'm going to pretend to be Michael Stadler. So if you came in a little bit late, Michael Stadler was going to join. Had some travel issues crop up and wasn't able to. And so
Before you go into here, could I make a couple of remarks?
Please do. This is Michael Stadler now.
Yeah, I've known Michael for a long time, from when he was at Berkeley, which is Michael Stadler, CTO of Zondi, has developed the most comprehensive model for microgrids and the integration of all these technologies, whether it's connected to the grid or not. And there are 25 items to rank the various models that are out there. There's a couple of dozen. And I went through that to find out what would be the best for this project. And there are 25 key ones. They can do all of them. The nearest one can do like 12. And this makes it a decision-making tool. And it's an optimization tool at the same time, that you can put any data in and it solves very, very quickly. So you could do lots of scenarios. This model was used to model an SMR at Idaho National Laboratory. So we had a generator, not just a CHP or flywheels for storage or anything else like that. We had the latest characteristics, operational costs, the characteristics for an SMR, put into this model. And we took this model and we brought it to the largest microgrid that we could find that had all of these characteristics with all of the data. This is real data we got here. It's the only place that it is and been modeled. So we got real numbers here. It's not just ideas. And then we modeled the entire campus, and then we decided that it would be a good idea to model the supercomputer itself. So all these scenarios and the benefit of all this, that's the evolution of it. But this is really state-of-the-art modeling for microgrid. And I think it's the only place where an SMR is included in an integration optimization model like this. Is that okay? That's what we want to take away from the
Perfect. Thanks, Michael. Hi, I'm Michael. Yeah, so, Zindi is a very powerful, system optimization platform. We loaded our data into it, and we use that to run out a bunch of different scenarios that, let you optimize your deployment to your metrics, whatever they might be. And for the sake of planting a flag, we picked a set of assumptions and generated some numbers, and we'll talk about those a little bit. So Michael with Zindi came up with a multi-step approach. So the single step is you just wait for the interconnect to come, or you wait for your SMR procurement to go through, and it's a path that'll work, but it'll take a lot of time. Can you wait for that time? And then the multi-year approach is there a right way to deploy assets that are available on the market now, in a way that you don't have stranded assets down the road when the nuclear reactor is on site, or is kind of standardly available. So you don't have to be a first of a kind project, but you can instead be the nth of a kind. And it turns out the multi-year approach has a lot to offer, where you can get your data center running now, and then you can be prepared for nuclear, when it's there. Here's the kind of the same idea in a different cross section. Phase one is like I said, just use technologies that's there. CHP with natural gas, use solar, use batteries, use wind, fuel cells, etc. So, some of these things you can go and have deployed in a matter of weeks or months even. And so, like I said, we wanted to plant a flag, get some numbers, see what the sensitivities are, see what we can learn. Probably not a surprise, we use the Blue Water supercomputer as our source of data. So this is, as I mentioned, 8760 data on both the thermal and the electricity and the cooling. We assumed a 10% annual increase, so you have your load. You keep getting more and more out of your data center as you go. We assumed natural gas increases a little bit, and then we focused on SMRs, natural gas, fuel cells, electric chillers, absorption chillers, solar PV, battery energy storage, and cold storage. Cold storage meaning that thermal energy storage with the chilled water. So for example, at the University of Illinois, our power rates went up a little bit during the day. So we would chill our water at night, so we'd have it available during the day, so you can get some significant savings that way. We made some assumptions on costs, we see at the bottom, and next we'll move on to what are the numbers. So basically there's three strategies for this. So one is utility only. This can have high costs due to infrastructure upgrades. You have total grid dependence. You have to wait for that interconnection. You have to wait for all that stuff to play out. Or you can just jump straight to SMRs, which again is certainly an option. Some folks are going down that path pretty aggressively, but it delays until your SMR's there. You have to basically be a first mover, which there's lots of advantages to being a first mover, and in nuclear we like first movers. But also perhaps a more pragmatic approach is a multi-year approach where you combine things, wait for things to play out, and you maybe don't get to reap some of those first mover benefits, but you will have a more certain project. So here are numbers from this analysis for 2025. Again, this is a kind of a phased approach. So we start off with natural gas at the cheaper end, not a surprise. Natural gas with an electric chiller, absorption chillers get you to a low cost point. I guess I should explain this plot first here. So the size of the bars indicates the size of the deployment, and then its position on the x-axis indicates the annualized cost of providing that energy. So this does not have the data center cost, but it does have the cost of providing energy. And so you see a pretty significant jump up after you move from natural gas to solar. And that becomes, if you're going to be completely dependent on solar, you need to do a pretty significant build out that's going to depend on where you're at. Maybe you've been to Illinois, maybe not. Illinois is not the sunniest place in the world. So that does require us to get a pretty significant build out with associated infrastructure that does drive up your costs. And then fuel cells over here get a bit more expensive. Fast forward to 2035, and the picture changes quite a bit. So in this case, the transition to SMR starts to be quite attractive. You can lower your costs with absorption chillers. Your electric chillers can provide your chilling at the cost of a little bit more electricity. But as I mentioned, you start to see the 10 to 20% reduction with absorption chillers should they work out. So that's what I have on that. But yeah, in conclusion, co-located nuclear power plants with data centers offers you some independence from the grid. There's some economic advantages, especially if you plan ahead. Depending on your applications, you select your technology, you work with your vendor. You optimize things, you can maximize the compute that you get out of there. And future-proofing your data centers, you can do a lot of planning where you can get deployed as soon as possible, be ready for SMRs as they come. You can avoid stranded assets with strategic investments. And here's some contact information. And I just want to leave on a note, in the nuclear industry, we are extremely optimistic. There's a lot of exciting things happening. There's large amounts of public investment. There's large amounts of private investment. There's very real technologies out there that have very advanced designs. There's real licensing action going on. The NRC is being very cooperative with licensing things at a very, very reasonable time. The optimism is high, but also it's not lost on us that it's incumbent on our industry to perform and to demonstrate that these things can be built and fulfill your power needs.
Bring the mic over when we have some questions.
That's turned on.
One more point, and then we'd love to have some questions of any sort. This study just was completed in February, and we're continuing to have findings from the modeling, and there's analysis focuses a lot on heat and the management of heat, and this is the major issue in the in the data center itself. And we're looking at this is an ongoing project that we have, and we're going to be talking about all the implications for heat as well. So why don't we take some questions? Questions?
Yeah, if you want to go to the mic.
Hi, Brice Zoku here, Head of Business Development at Radiant. We're developing a 1 megawatt nuclear microreactor. Are there any kind of unit cost projections on the nuclear side that you guys are willing to share?
Yeah, we don't have any data that we can release that's not publicly available. I guess that's kind of an obvious thing. But yeah, for our reactor project, those costs are going to be proprietary. But in some of those reports that I cited, they do drill down to what a unit might cost. But yeah, there's a lot of uncertainty there.
Thanks for your presentation. So what I see is, being an ex-hyperscaler myself, building data centers, the risk is being put on everybody else. Hyperscalers don't like risk, right? They like profit, just not risk. And then we have the grid, which is also not really liking to take risk. But there's this huge opportunity in between, and of course there's nuclear as a solution. In a previous another presentation or at the keynote, David's talking about natural gas as a solution. I think the real opportunity is at the seam of those two, and maybe this is what you're calling the microgrid, but it's really about energy as a service. As a hyperscaler, I really don't, pardon the expression, give a shit what the power is, as long as you meet my requirements, right? Whether, you know, I might have requirements on availability, I might have requirements on cost, I might have requirements on carbon content, et cetera, et cetera. I think there's this huge opportunity for integrators who will integrate the different technology and give the solution. But I don't see much discussion about that. So I'd love to hear your thoughts on that.
Absolutely, and I totally agree. It's a bit tangential, but I like to say the feeling that we get from industry is people are going to line up to be second. You know, the opportunities there, people just don't really want to take that first mover risk. So this is part of the reason that we're doing our deployment on campus, is we want to take some of that first mover risk because we derive a lot of research value out of it. We don't necessarily need kilowatt hours to recoup our costs. And toward that, developing the integration, you can you can really reduce your cost basis by fulfilling your application in the most efficient way. I feel like I'm talking around your question. Am I getting close?
Well, I think it's around the integration of natural gas, renewables, nuclear. Nuclear is more time-based because you can't get it right away, but you're short-term. At the end of the day, at the end of the day, as the end user of the power, I don't want to be involved in the complexity of how you're doing, right? Having someone come in and say, we'll end on nuclear, but we'll start on something else, and along the way, this is the cost of what it's going to be for you. And someone that takes all that risk and packages it in a way that kind of mitigates the risk is where I think there's an opportunity, and I don't see much work about it. It's either about a singular technology and why it's great versus, I think they're all great, but they have their place. Nuclear doesn't have its place today, but it will in the future because it takes, you even said yourself, 5 to 10 years. Natural gas is maybe available now, but then even short term, there might be ways to become flexible loads, right? There's no real discussion around that middle space being more as the integrator. I mean, I would see that's a huge business opportunity.
Integration is the major focus of what we're doing in the Power Engineering Society, integrating everything that you talked about, and to optimize that around costs where maybe you just have for certain data center loads that are super, super critical and others that may not be and integration is all what this optimization is about. The microgrids and the modeling tool for that is the tool for integration. And it tells you what the optimum combination is for a given load profile. That's exactly what we're talking about. Integration of renewable energy, flexible loads, flexible demand, markets, whatever the price is. Princeton Microgrid actually stops when the price of power from the grid goes down and it starts up again. CHP is combined heat and power. And one of the most promising areas for integration is the area of heat. We want to use some of the heat. And that's a very promising area. And also the fuel diversity. That's another huge area that we want to do with, and it gives a lot of security. So you know where we're trying to go on the power side very, very well. No one's there doing it, though. No one's there doing it there. Oh, you got that.
Yeah, I'm going to keep thinking about that. Thank you.
Hi, guys.
Hi.
Thanks so much for your speech today. Mark Heineman, Fire to Fission. We are a project integrator, so timely. We're doing natural gas today and nuclear tomorrow, fire to fission, right? So let's chat afterwards. 2 questions for you guys. Love the presentation, Michael. You did a great job. Do you see an ideal power system size in kind of all the work that you guys are doing? Is it 5 megawatts, 100 megawatts, 500 megawatts? That's question one. Then question two, what are some of the biggest risks that you see with this integration of kind of one power system today and then transitioning to nuclear tomorrow? Thanks.
Yeah, thank you. To the first question about the ideal size, that's going to depend on your application, and there's some uncertainty there. So if you would ask this question, 40 years ago to a nuclear engineer, they would have said as big as possible. And then they to maximize economies of scale, so they built these gigawatt scale plants that power millions of homes, and they work great, but they became very, very complex to operate. And so we learned that those construction projects became very significant. And so you see folks trying to take lessons learned from that to make simpler construction projects, which is the AP1000, another gigawatt scale reactor. But then you see folks across the spectrum that are trying to bring some of that construction in-house to centralize some of the manufacturing and drive that construction project down, drive that construction risks down.
A number of vendors have been playing with this over time as the sizes of the hyperscalers have appeared. One of the most visible of the vendors, who can't mention the name, they were starting out with 20 megawatt modules and then add them together according to what they wanted. Another one started off at 5, and now they're at 77 is their ideal basic unit to fit with others. And it's all over the place. It goes from 1 megawatt to 5, and then we're going to add them together into certain size groups or whatever, or it's optimal if we work with 177 one, which is a very odd number. So a lot of vendors are trying to follow that when they finally get all the approvals and ready to do something, they'll have the right size one to add together and make whatever's best for the industry. We're taking a little different approach. It's your approach of integration. What's a unit to start with and succeed with that can be married up with something that's proven concept that can supply a service reliably today and work integrated with the grid. So that answer is all over the place what the size should be.
So yeah, basically, every vendor has a really compelling case as to why they're designing the size that they are. Sometimes it's application dependent, and on the other side, we'll see. For your second question, I kind of gave away my answer in the first part. Is if you're going to start on a project now, I think the biggest risk to your project are the construction timeline and the licensing timeline. So we have folks making real progress on both of those. There's a lot of licensing engagement happening. It's very successful. The NRC is looking like they're going to play ball. They're beating a lot of the deadlines, at least in my interaction with them. But at the same time, we're only in the construction permit application in most cases. The operating license, there's some undeterminism there that we need to wait on. The nice thing about both of these risks is these demonstration projects that I referenced are going to collapse those risks in the next few years. So we'll keep watching.
2 more minutes. This woman's been standing there.
Oh, yes, please.
Hi, my name's Holly Elwood. I'm from the Global Electronics Council. We manage the EPEAT eco-label for sustainable servers and network equipment and soon-to-be data storage equipment. I was just curious if you could talk about what you see as steps people need to take when they're committing to nuclear in terms of dealing with the waste at end of life, and what you're recommending for a strategy.
Sure. Yeah. Good question. So I'll start off from a technical point of view. Nuclear waste doesn't really bother any of us on the nuclear side. It's the storage casks that we have right now. We put them in there. It's very safe. It's very secure. From a policy side, there's certainly some questions there. If I had to guess, there's going to be some independent fuel storage locations which will take them. Currently, what happens is all the major reactors, they just keep everything on site right now. The fact that nuclear waste is such a small volume gives us a lot of advantages there. And yeah, some of this will be determined if DOE starts taking title to the fuel like they're intended. Otherwise, it looks like there'll be some kind of interim storage kind of as a service opportunity. It is part of a license that you do need to have a plan for that, though. Yeah.
Yeah, thank you, Michaels. My name is Bruce Anderson. I'm CEO of 24/7 Solar. And that's what it means. Every single hour of the year, we provide electricity, and we provide heat to drive absorbents and chillers. Very high level of reliability. So my question has to do with reliability. When an SMR goes down, what's the backup?
Yeah, this is a really good, a very good question. And there's this research to be done here, but there are some applications where you'll pick pick a data center application that can handle waiting for the refueling, for example, the couple weeks to refuel, or you just rely on grid backup. So in that case, your the time to get a reactor, your interconnection's gone, you have grid backup. I think the cases that we, Michaels, simulated here use natural gas for the backup. So you'll have a generation portfolio.
Yeah, I mean, that's pretty awkward. If you're adjacent to a grid that doesn't have the capacity and your SMR goes down, what's the data center supposed to do? The other question I have around SMRs is the flexibility to meet flexible demand by the data center. The last I heard, they don't operate that flexibly. What do you do with that?
Yeah, so ramp rates right now are fairly slow. This is mostly a regulatory limit because at baseload power you don't need to ramp very much. So new technologies are getting increased ramp rates if that's their design. There's also energy storage, energy storage options that help with that. For example, our deployment's going to use a molten salt, a small molten salt thermal energy storage that will absorb those peaks without a problem.
Storage with nuclear is one of these integration issues. It's very, very, very important. It's important for other things too, like transition functions and stability and all sorts of things. And marrying this energy storage with the UPS with multiple sources of generation is where you're going to get your most reliability. And that's what we're working on for this integration question.
So we'll take one more question, and then I'm happy to catch up with anyone in the hallways. Sorry.
Hi, Guillermo Wire. I'm with Bluefin ESI. We are actually IP holders for the cleanest burning diesel engine on the planet. But as part of that, one of the focuses we have been spending a lot of time on is AI performance. And typically, I've been involved in a lot of microgrid discussions, and we see turbines as being not as robust in performance for AI workloads, dynamic workloads. And is there any testing on SMRs for AI workloads today? Do you plan on doing that on your prototype project? And I know you mentioned battery storage as potential supplement to help smooth that out, but I'd be interested in hearing that from you.
Yeah, so this is exactly the kind of operational research we're going to do with our facility. Is what is the optimal way to do that? So certainly you can buy as much storage that you want to meet whatever fluctuations that you need, but that's increased equipment, that's increased cost. So there's going to be some optimal. Let's ramp a little bit at this time to fill the storage here, and then we've also looked at job schedulers that work on that kind of on the back end. But yeah, that's exactly the kind of research that we plan on doing to make sure that we can.
With that, I think we have to.
Great job. Thank you.
Can we thank Michael?
Good job, Michael.